So it's my pleasure to introduce Kaitlyn Rivers. She worked on a project this summer with Ed Rutherford, Doran Mason, Hank Vanderploeg, and David Wells. So Kaitlyn, I'm happy to turn it over to you and let you introduce your talk.
All right, thank you, Mary, and hi, everyone. Again, my name is Kaitlyn. I just received my bachelor's degree in biology from Oberlin College, and I'm on my way to the University of Florida for a graduate degree in wildlife ecology and conservation. And as Mary said, I worked with my mentors, Dr. Doran Mason, Dr. Ed Rutherford, and David Wells. And today we'll be talking about shifts in diet composition and food consumption in larval alewife, bloater, and yellow perch. So a little bit of context for this project. Larval fish growth rate is extremely dependent on water temperature, prey availability, and prey selectivity. And since 2010, the larval fish growth rate in Lake Michigan has been declining by 33 to 50%, even though the factors such as water temperature has remained steady over this time frame. But if we compare 1983 to 2015 temperatures seen in the right graph, the dark blue dots being 1983 and the lighter blue dots making a line for 2015, we see that there is a warming trend throughout the entire water column, especially in the surface area and the epilimnion region. There has also been a decline in zooplankton biomass, which Holling's fellow Gina Scott presented yesterday. And I'm sure you guys are familiar with the invasion of the Dreissena mussels in Lake Michigan as well. So first, the zebra mussel, which has been found in all Great Lakes by 1990. And the image to the right shows a graph of the density and distribution of the zebra mussel in Lake Michigan from 1994 to 2005. And we're seeing a similar trend with the quagga mussels, which have been found in all Great Lakes by 2005. And again, the same density and distribution graph up until 2005 shown below. And the quagga mussels have actually started replacing the zebra mussels in certain areas of Lake Michigan. And the invasion of these Dreissena mussels has caused changes in available light throughout the water column in the lake, changes in biomass and distribution of primary and secondary producers, as well as changes in nutrient cycling and availability. And for this project, I am mostly focused on the Veliger, which is a free swimming planktonic stage of these mussels. These are the three species of fish that I analyzed for this project. First, the alewife, which is a pelagic planktivore, and their larvae are primarily found in the near shore zone of Lake Michigan. And their population has been declining since the 1970s. Next is the bloater fish, which is a deep water planktivore, and their larvae are found near shore and offshore of Lake Michigan. And their population has been declining since the 1990s due to competition for food with the invasive mussel species that we just talked about. And lastly, the yellow perch, which is a generalist feeder in Lake Michigan, found as larvae in the nearshore and offshore zones. Their population has been declining since the 1990s as a result of poor recruitment, as well as prey competition with these mussels. So all of these larvae were sampled along a nearshore to offshore gradient in Lake Michigan off of the Muskegon area. So the zoomed in box to the right shows the three offshore gradients, M15 being the nearshore zone, M45 about the intermediate, and M110 being the offshore site for sampling. The larvae were sampled in 1983 and 2015, which are my sample years that I'm concerned with for this project, using Tucker trawl, Newson, and bongo nets. The Tucker trawl is an opening and closing system seen here on the right, and the bongo net is a double net system for plankton surveying. And the Newson net samples the surface waters. Both sample years identified fish to the species. At the top right, we see a yellow perch larvae. And both sample years analyzed the diet contents using the stomach. So right here, we look at copepods that have been found in the stomach of the larvae. And in 2015, they went a little extra and they extracted the otoliths from the larvae and counted rings to get an estimate of growth and as well as age. So I've laid out a trajectory for this project. First, we'll look at whether there was a difference in size between 2015 and 1983 larvae. This graph shows length in millimeters of the observed larvae, split into sample years and by catch month. There were no larvae analyzed for diet contents in August of 1983. And while this graph only shows alewife larvae, the mean length of all three species I analyzed in 2015 was less than the mean length of the 1983 larvae, with the exclusion of the August group because of lack of comparison. Next, I calculated growth rates of the larvae using a mean length from each species in 1983 and 2015. This graph shows growth rate in millimeters per day on the y-axis, and we can see that the growth rates of the 2015 larvae across all species is less than the 1983 and 84 larvae, given the length of the time the model was run, as well as the estimated hatch dates that I input into my model, which we'll talk about a little bit later. So the big question is this change in growth rate due to temperature changes in Lake Michigan, or is it a result of diet composition changes because of the post-Dreissena mussel invasion? So now we'll determine whether temperature or diet composition is the confounding factor. And to do this, we'll start looking at the difference in consumption values between the sample years that I'm using. To do this, I ran a bioenergetics model called FB4. The models are using an energy balance equation to calculate consumption being C in this equation below, and growth rate, or G, in this equation is a function of what is taken in during consumption and what is lost due to excretion, which is U, and respiration, which is R. And the output consumption value for my project is a p-value, but I want to note that this p-value is really the proportion of max consumption, not a statistically significant value. But it is to note that any value from the model greater than 0.5 implies greater feeding rates because of things such as favorable factors like prey quality or prey abundance in the lake, as well as higher energy levels based on the prey species, as well as water temperature. And any increase in food consumption for the p-values could mean that we're seeing greater growth rates in my larvae. So we'll look at Alewife to give this comparison first. On the y-axis is the p-value, again, the proportion of max consumption. And to account for older and larger individuals in my samples, we split the larvae into catch dates for cohorts when applicable, and this is seen on the x-axis here on the graph on the left. And in 1983, the most abundant prey item for Alewife was the calanoid copepod, seen at the bottom right. And in 2015, only 3 larvae out of the sample of 88 had diet content, which is about a 96% of my sample having empty stomachs. And we'll talk about that significance later. And because of this, those 3 individuals were run as a population, which you can see on the x-axis of the right-hand graph. But all 3 of these individuals had veligers in their stomach as the primary prey item. And since there are veligers, I ran the model once with a high energy value seen in the orange bar, and once again with a low energy value seen in the blue bar. Because we don't have a definitive energy value for the veliger, it was good to run both so we have somewhat of a range of consumption for these individuals. But for Alewife at least, no matter the energy density of the veliger, the 2015 larvae are consuming less than the 1983 larvae, which is probably evident when I said 96% of them had empty stomachs. Next is the bloater. The blue bar shows the 1983 larvae, and the orange bar is the 2015 larvae. I chose to only compare July in this graph since it was the only month that overlapped between the 2 sample years. And for 83, the most abundant prey item was again the calanoid copepod. But in 2015, the bloaters switched their diets to primarily copepod eggs. And it is to note that bloater do not consume veligers, which is what was found in my sample, because their early and adult life stages are primarily offshore for this species. With that being said, overall, the 2015 larvae are consuming more than the 1983 larvae. Lastly, we'll look at yellow perch. There were no yellow perch with diet contents from 1983, so I used 1984 larvae instead. And again, I chose to only compare the July cohorts because that was the only month that overlapped between the 2 sample years. And again, the most abundant prey item in 1983 was the calanoid copepod. But in 2015, like the Alewife, their diet was mostly composed of veligers. And like Alewife, I ran the model twice to account for the veliger energy density difference, with the middle bar being the low energy value and the right bar being the high energy value. So if we assume a low energy value seen in the middle, the larvae from 2015 are consuming more than the 84 larvae. But if we assume a high energy density for the Veliger, they're eating about the same. So for, at least for yellow perch, it's very dependent on the energy density of the Veliger to estimate consumption values. So going back to the main question of this project, is the difference in growth rates based on the 1983 and 84 compared to the 2015 larvae a result of temperature changes in Lake Michigan, or is it a result of diet composition shifts in the larvae post-Dreissena mussel invasion? So first, we'll look at the effects of temperature changes on the larvae. Again, if we have the proportion of max consumption or the p-value on the x-axis or on the y-axis, and for alewife and yellow perch, which have veligers in their diet, the values were split by low and high energy values seen on the x-axis here below. So with this graph, if we keep the 2015 diet composition, but vary the temperature, with the blue bar being the 1983 temperature, we see that there is an increase in proportion of max consumption, or the p-value, for alewife larvae caught in 2015. This trend is also seen when I run the same model on the yellow perch from 2015. But for bloater, the 2015 temperatures were taken from the hypo and metalimnion, since that's where bloaters primarily were caught. But in 1983, the larvae were found mostly at the surface. So we took surface temperatures to represent the 1983 blue bars here. And when as I mentioned, or as was mentioned by Holling's fellow Gina Scott yesterday, if you saw her presentation, warmer temperatures typically cause an increase in metabolism, resulting in an increase in consumption. But inputting the warmer 1983 surface temperatures with the 2015 diet composition actually varies the proportion of max consumption for bloater larvae. We see an increase in consumption for the August cohort, but a decrease in consumption for the July cohort. And it is to note that the August cohort was significantly larger in size than the July cohort. So lastly, we'll look at the effects of diet composition on larvae consumption to figure out which is the biggest confounding factor. Now, when varying the diet composition, but keeping the temperature profile constant, on the left graph we have 1983 temperatures as the constant, and on the right we have the 2015 temperatures as the constant. We see very little difference in consumption for alewife larvae between the two diet compositions. You can see between both bars and both graphs. And this is true no matter if we keep 1983 or 2015 temperatures constant. And this is also true given the energy value of the Veliger. Right now, these graphs show low energy density, but the same trend is true when I use a high energy density as well. And this graph shows only, this is for yellow perch. If we vary diet composition but keep the temperature profile constant, again, the 80s temperature being on the left graph, and the 2015 temperature being on the right graph, this actually does show a difference in consumption for yellow perch. The yellow perch are the anomaly here. So some final remarks regarding all of this. For all species, the mean length of larvae analyzed for diet compositions was greater for the 1980s larvae than the 2015 larvae. And for all species, the 1980s larvae have greater growth rates in millimeters per day than the 2015 larvae. So going back to the biggest question, diet compositions have shifted from calanoid copepods in the 80s data to Dreissena veligers for the alewife and yellow perch, but then for copepod eggs for the bloater. And as mentioned by Gina Scott yesterday in her presentation, and I mentioned earlier in my presentation, the zooplankton biomass in Lake Michigan has dropped since 1983, which may be why we're seeing diet composition shift for these larvae species and potentially other larvae throughout the entire lake. And I also want to reopen something that I said earlier, was that 96% of my alewife sample had empty stomachs, which could mean that they're not thriving, or they may even be starving throughout their life cycle. And going back a little further, even though I saw that changing the diet composition and keeping temperature constant does show a difference in consumption values for yellow perch, there is still a large difference when we look at the temperature being varied and diet held constant. So with that, I want to say that the model shows that temperature is the confounding factor affecting larvae consumption and also potentially growth rate more than the diet composition for the larvae that we analyzed. I'm sorry to say that, Ed, it doesn't seem that the Veligers are having a great impact, but they might be having an impact nonetheless. So some future work to go with this project. I think it's important to continue monitoring the larval fish growth rate as a function of diet composition and temperature shifts in Lake Michigan post-Dreissena mussels. And since this is a preliminary run of the bioenergetics model for these fish species and the mussels, it is important that we run the model later with a definitive value for the energy of the Veliger so that there are no outliers and there's no if, ands, or but. And with that being said, it is important to continue monitoring alewife populations. Alewife are considered to be a very important species to Lake Michigan due to their dual role being a predator and prey for the salmonoid fisheries system. And again, 96% of my alewife had empty stomachs. And if the alewife population continues to decline because of starvation and lack of prey, the bloater population could increase as a result of the alewife collapse. So lastly, I just want to round it out saying some of my acknowledgments for all of my people, my mentors, Doran Mason, Ed Rutherford, and David Wells, especially David for being on call almost every day throughout this process. Anna Schnitt for her help with data organization as a technician for us. Nash and Geffen, who supplied me with the 80s data, as well as Gina yesterday with the 80s data and answering so many questions about what was going on with their spreadsheets. And then lastly, CIGLR and Mary Ongle for the support and the opportunity, as well as NOAA and GLERL for this amazing opportunity. I never thought a virtual fellowship could be so exciting and so great. Thank you.
Thanks so much, Kaitlyn, and thanks for the kind words. We've all been pretty flexible in this virtual world, and I'm just so happy that it was to hear that it was a good experience for you. And great job on your presentation. Really impressive work.
Thank you.
We have one question that's been typed in the box from Hank Vanderploeg. He says, nice job. How does the bioenergetic approach deal with the zooplankton abundance?
So there is an option for the bioenergetics model to input invertebrates. I specifically didn't look at that. I think for me, the biggest input for zooplankton biomass is the count of prey items that my fish have in their stomachs, which is one of the external factors that I set into the model, into the R code for it to script. So I have a proportion of all my prey items saying, okay, they ate 50% of this and 10% of this. And that also corresponds to that energy balance equation showing, okay, if they eat 50% of Veligers and out of their diet, Veligers have the highest energy content, then that shifts their growth rate and also shifts the respiration rates and other things like that they're assuming. But at least on my end, it's not a direct correlation to zooplankton biomass. I think Gina's presentation yesterday did a better job at looking at the biomass at depth and also at certain sites that I investigated.
Great, thanks so much, Kaitlyn. And Hank, if you have any follow-up questions, feel free to raise your hand or type another one in the chat box. I see that Philip Chu has a hand up, so I'm going to unmute you, Philip. Philip, you can go ahead and talk.
No, sorry, I did that wrong. I meant to, I don't mean to raise my hand.
Oh, okay, no problem. I'll remute you. Okay, at least I was able to successfully unmute him though. Okay, looking to see if anything else is coming in here. Right, I don't see any additional questions, Kaitlyn, so we'll go ahead and move on, and if someone has something else, if we're moving on too quickly, they'll type it in and we can come back to it next. So thanks so much, Kaitlyn, and you can go ahead and stop your screen share.
All right.